So the first thing we want to do is to develop three-dimensional wave equation. So okay, let's recall the one-dimensional case. So we had a very long rod and we only considered the longitudinal wave propagation. Okay, let's recall where we started there. So we took a small element out of the very long rod. So the element length is dx. The cross section is A. So if we look at this element, the forces which are applying on this element are in the longitudinal direction. We have, let's say, stress in the x direction, longitudinal stress, normal stress, however you like to call it. And on the other side, we write it in the most general form. So to the left, if it is sigma x, to the right, it would be something different. So we write this difference generally in the form of sigma x plus the change in sigma x in the direction of x, right? And this will be multiplied by A. And then we also have the inertia, which acts opposite to the direction of movement. So if we assume that the positive x direction is to the right, and also the displacement in the x direction u and the acceleration in the x direction are also positive, so this will be m u dot, and then we show that you can write m in terms of density times volume of this differential element, which is a dx. Now, if we write the equilibrium, the dynamic equilibrium for this element, we have in the positive direction the change of sigma x in the x direction, in the positive, in the horizontal, let's say the change in normal stress in the x direction. And then we also have negative inertia, which would, when we cross out a dx, we'll have rho u dot. I seem to have forgotten here to write u dot. So this is basically m, this one thing. Okay, so this has to be equal to 0. And then because the motion in time is harmonic, so we can easily say that, okay, so the acceleration is negative omega squared u, and this brings us to the wave equation in one-dimensional case, where we had the change in sigma x with respect to x is equal to rho and negative omega squared u. So we write it negative rho omega squared u. So this was in the one-dimensional case. So all we want to do right now is to extend this formulation to 3D. So in 3D, we don't have only x direction. We'll have x, y, and z. And we also take the positive displacement in the x direction to be u, and also that u dot will be also in the same. It will be the positive the positive for u dot will be in this direction. So actually, basically u dot, but we call this u. And in the y, it would be v double dot, and in the z, it would be w double dot. So we use u, v, and w for particle displacement in x, y, and z directions. So instead of having a square element, then we have a cubic element. And so the dynamic equilibrium equations will be 3, because along x we can write the summation of forces, but we can also write it along y direction, and we can also write it along z direction. So we we just write it. I don't really want to go through the details as I told you in the class, but this is easy to see. It will be an extension of what we had before. So for sigma x, it will be the same. Then we have a term which is sigma xy. And then we have sigma xz, the derivative with respect to z. And on the other side, we have negative rho omega squared u. So this is the same as saying rho u dot. They're the same. And remember that u is particle displacement in x direction. So along y and z direction, the expressions will be very similar. So you can try to see if you can write it yourself. Pay attention that this x could be like xx. We just, for simplicity, we write it x. So then we have y with respect to y, and then we have yz with respect to z, and here it would be negative rho omega squared v, which is the same as saying rho v double dot. So v is particle displacement in y direction. And then when we write the equilibrium along the z-axis, we have here zx with respect to x, then we have zy with respect to y, then we have z, or you can think about it as zz with respect to z, minus rho omega squared w, or rho w dot, where w is the particle displacement in the z direction. So these are the equilibrium equations that we have. So and sigma x, sigma xy, sigma xz, the rest of the sigmas are of course stresses. And we know that sigma ij is equal to sigma ji. Basically sigma xy is the same as sigma yx, and you can very easily visualize this cube, which now the lengths are, here is dy, dx, and dz, and this would be like sigma x or sigma xx, and for example here would be the component, the way we named it, sigma xy, so it is acting on the face which is perpendicular to y. However, the direction is x. The same way here, if we have here a component which is acting on the face which is perpendicular to z, but it is in the x direction. So you can see that when you write the summation of forces in the x, all of these components, they sum up together, and you can make the same argument about the other directions. Okay, now that we have dynamic equilibrium equations, we have to try to relate stresses to displacement. So if you remember the wave equation, at the end it relates the displacement u, the derivative with respect to x, to the derivative with respect to time. So in one-dimensional case, you may remember that what we got was Vp squared, the second derivative of u with respect to x equal to the second derivative with respect to t. So we don't see any stress here. So our goal here is the same. We have to get rid of a stress, and for that we have to go step by step. The first thing is we look at the relationship between a strain and displacement. So in one-dimensional case, this relationship was straightforward. The normal strain is the change in displacement for unit lengths. So mathematically, we can write it as the derivative of u with respect to x. In 3 dimensions, things are not that much different. So for normal strains, basically the same thing. The x direction is the change in the displacement, the x direction per unit length. In the y direction, it is the change in displacement in the y direction with respect to the length, and in z direction we also have very similar expressions. Now in 3D we also have shear strain, right? So gamma xy can define it as the derivative of u with respect to y plus the derivative of v, which is displacement in the y direction with respect to x. And very similarly for yz and zx. Let's write this nicely. And we quickly discussed this in the class in case you don't remember. Let's say if you take one of the planes, let's say YZ, we can look at the symmetric definition of shear strain. So if this is the original undeformed element, once it deforms, it becomes a diamond-shaped element like that, and the shear strain is defined as the change in the angle. So basically gamma yz is the summation of 1 plus 2. So we can see that the gamma yz1, it is the derivative of w with respect to y, and the other one is the derivative of v with respect to z. So that's why these expressions are coming from. Okay, now we are not done yet, and now we can express strain in terms of displacement. But remember, in the equations we have a stress, so the next natural step is to relate a stress and strain, which basically we go back to the material model. So in this class so far we just considered linear elastic materials. So in one-dimensional case we used the Hookes law, very simple, sigma x is E epsilon x, and then because we have now the strain displacement relation, we can go from a stress to displacement, as you can see. So we want to do the same thing in 3D. So in 3D we have to write the generalized Hookes law, the so-called generalized Hookes law. In general, we want to write the constitutive equations. Constitutive stress strain relations. And here we consider a linear elastic material. So linear elastic. And we need to write the generalized Hookes law. So how does this law look like? Well, it's very simple. What comes into play is Poisson's ratio. So writing epsilon in terms of a stress, we have epsilon x is 1 over E sigma x, and then minus Poisson's ratio nu sigma y, and the same for sigma z. And of course this is Poisson's ratio. And the same we can write for epsilon 1 y and epsilon z. I write it very quickly. And the shear strains are even simpler. So sigma xy is just g times gamma xy. So the relationships are very simple. So very quickly I write all three. We have to write here sigma zx over g. Okay, so now that we have the stress strain and a strain displacement relation, we are almost ready to go. However, we still need to introduce some parameters which come very handy here. One parameter is volumetric strain. So we introduce some parameters you already know. One is volumetric strain. We use E here, which is just the summation of normal strains, which is epsilon x plus epsilon y plus epsilon z, and consequently we can write it in terms of displacement, the derivative of u with respect to x plus the derivative of v with respect to y plus the derivative of w with respect to z. So this will be one important parameter. The other one are the rotational strains. So they also come very handy. So if you look at the previous slide, if you look at here, if we think about x-axis, so the x-axis is kind of sticking out of the plane towards me that I'm talking. So we can consider that, you know, this element is rotating about the x-axis. So if I ask you how much it is rotated, what would be the answer? So let me rephrase my question. So if gamma yz1 and 2 are equal, there is shear, but there is no rotation really, right? It's not rotating. But if one is bigger than the other one, this is actually rotating. So in one direction or the other. So here, for example, rotation about x-axis, you can see that we can define it as the derivative with respect to derivative of w with respect to y, which is gamma yz 1 pretty much, minus the derivative of v with respect to z. So this is kind of how much it is rotated. So we use 1/2 in the definition to define kind of a new parameter omega x. So the concept is related to the rotation about different axes. So if we define omega x 1/2 of the derivative of w with respect to y minus the derivative of v with respect to z, we can do the same for y and z. Now, to remember how it goes, it's sometimes helpful to have this kind of clockwise rotation, meaning that when we want to write for y, the denominators would be z and x, and when we write for z, the denominators would be x and y. This is important because we have a negative sign, so we can't interchange the two terms. So then it is easy to see how it would look like. So these are kind of our definitions for rotational strains. As we explained before. Now all we have to do is in the dynamic equilibrium equations that we derived in the beginning from the free body diagram in 3D, these are all, they had a lot of stress terms in them, so we have to change a stress. We use the constitutive models to relate a stress to a strain, and ultimately we use a strain displacement to go from stress to displacement. So the sigma ij, we basically want to write everything in terms of u, v, and w. Now I don't really want to show you all the details, but if you do that, this is what we are going to get. We'll get, of course, 3 equations for 3 directions. And they will look like that. Lambda plus 2g the derivative of e with respect to x, and then we have 2g, and this term will be in terms of rotational strains. So the derivative of omega y with respect to z minus the derivative of omega z with respect to y. And this would be rho u dot, or negative rho omega squared u. And we can similarly write this in for the other directions. So let's do this very quickly. So remember that E here is volumetric strain. Hopefully I didn't make much mistakes here. No. So these are the three equations that we have. And if you want to compare this to the one-dimensional case before, there we had, in one-dimensional case, we had E, and then we had the second derivative with respect to x. This was equal to the second derivative with respect to t times rho. So let me write it a little bit nicer, rho u dot. So this is kind of comparable to this equation you have seen before. Now there is some new parameter here, so we don't see E and we see this lambda. You may have heard of lambda, this is a so-called Lamb's constant. And its relationship with E is basically a function of Poisson's ratio. And so lambda plus 2g is called constraint modulus. So constraint modulus, and it is 1 minus nu E over 1 plus nu 1 minus 2 nu. So now we are not there yet. So if you look at the wave equation in one dimension, we have a double derivative with respect to x also, but here we don't have it yet. So how do we get there? It's pretty simple. So what we have to do, we have to kind of separate the volumetric strain from the rotational strain. So the change in volume is basically associated to compressional wave propagation. So now we want to separate these two parts. So first we want to focus on compressional wave propagation. To do that, we kind of have to get rid of the rotational strain. So the way to do it is, if we get a derivative of equation 1 with respect to x and sum it up with the derivative of equation 2 with respect to y, and then also sum it up with the derivative of the third equation with respect to z, it's going to give us, we are basically going to cancel out all the rotational strains and we'll be left with this equation. If we sum everything up, m, the second derivative of u with respect to x, the second derivative of, e, with respect to y, second derivative of e with respect to z, is equal to, so then we have the first derivative of u with respect to x, the first derivative of v with respect to y, the first derivative of w with respect to z, which is nothing else but the volumetric strain. So basically, if we use a more compact notation, we see that m del 2e, this is a compact form to write these three second derivative terms together, is equal to let's say rho e double dot, which we wrote it like that. So basically we are saying that E is in time has a form like that, harmonic. So this is very similar to in 1D. If you recall, we had E second derivative equal to rho dot, so which is also like that. So this is one-dimensional, and we have a similar equation in 3 dimensions. So this equation, as you can see, involves the volumetric strain, and the solution basically describes the propagation of compressional waves. So very similar to what we said in the one-dimensional case, that E over rho had some meaning. So in one dimension, we said that, okay, the velocity of propagation of compressional waves would be square root of E over rho, right? So here in 3 dimensions, it is also very similar. So in 3 dimensions, the velocity of propagation of compressional waves is m over rho, where m is the constraint modulus, so lamb's constant plus 2g over rho, and this is greater than E over rho. So in other words, compressional waves propagate faster in 3D. So if you look at a 1D or 3D, you may have in the same material, you'll get different velocity of propagation. This is an important fact, and to remember. So this is Vp is the velocity of longitudinal wave propagation in the bulk of material. So this confinement of particles by neighboring particles make the wave travel faster. So that's an important conclusion. Now, what happens with shear waves? So next is we look to see, what can we say now about shear waves? So just to basically spoil the whole excitement, I tell you up front that the velocity of shear waves is the same whether you do it in 3D or 1D. You will get the same value, which has some benefits, because if you want to upscale, it's much easier, right? Because you just it's the same no matter if you take a long rod or if you don't. So how do we get to that? It's pretty simple. Now, if we take the derivative of equation number 3 with respect to y, and then we subtract from this the derivative of equation 2 with respect to z, this way we can get rid of, we can eliminate anything related to volumetric strain. So we will get G, shear modulus, G, and then the second derivative of rotational strain about x-axis with respect to x, the second derivative of rotational strain about x-axis with respect to y and z, and this would be negative rho omega squared rotational strain omega x. And now we use a compact notation again. So del 2 del squared. So this operator is called del 2 sometimes, del squared, Laplacian, and then here is a vector of omega x, omega y, omega z. So this would be equal to this is general when we have everything. This would be equal to rho double dot, which we can write as negative rho omega squared so these are this is a vector of omega x, y, and z. This is and again, recall that this has a very similar form to wave equation in 2D, so we can easily say that, this is the Vs squared, this is the propagation of shear waves in 3D, del 2 omega and here would be plus omega squared. We are bringing it to this other side. So of course Vs is square root of g over rho. Shear wave velocity in 3D, and you can very easily see that it's equal to Vs in 1D. So it doesn't matter if we use 1D or 3D, shear wave stays the same. An important conclusion. So we don't even have to say if we measured it in 3D or we measured it in 1D. And okay. So the last thing to say before taking a little break is to look at the ratio of the P wave to S wave. So this ratio is in 3D is as we saw, so here we have m over rho and here we have g over rho, and m is lambda plus 2g and here we have g, and if we substitute for these two parameters, for constraint modulus and g, we get this ratio, which is 2 minus 2 nu being the Poisson's ratio, over 1 minus 2 nu. So let's say for concrete we have nu is about, let's say, 0.25. So this ratio is 2 minus 0.5 and then 1 minus 0.5. So here is 1.5 over 0.5. So it's about 2 times. This is typical. First of all, the P wave is the fastest wave propagating within a bulk of material, and in concrete, in rocks, it's kind of normal to have this kind of ratio, about 1.5 to 2 times larger VP, compressional wave velocity, than shear wave velocity. And also it's interesting to note that this ratio is only a function of Poisson's ratio, meaning that if we can measure V sub P and V sub S, we can actually measure the Poisson's ratio non-destructively. So by measuring V sub P and V sub S, we can obtain Poisson's ratio non-destructively. Okay, so in the next video, I talk a little bit more about the solution of wave equation. So a little bit more details about what it all means. Okay.